the Norton RL circuit. The analysis of an RL circuit is exactly the same as the RC circuit analysis. So I'm not going to reinvent the wheel. So we know already quite a bit about this. So let's summarize with highlights of our RC analysis. So the first thing we have to do is that we have to convert a RL circuit into a Norton RNL circuit after the switch is thrown. So if I use the original circuit that we did for RC, it doesn't matter because they're going to look all the same. I'm going to say that I have my source, just like we did before. I have a series of resistors. Which are labeled R1, R2, R3. But this time, we have an inductor in the circuit instead of a capacitor. So here's our inductor, and our whole goal is to determine the current of this inductor. And just like we did last time, we're going to have a switch. So when this switch closes at t equal to 0, we then focus on what we need to do. So if we truly do a source, not a source transformation, but we calculate the Norton equivalent, then this is what we're going to get. We're going to get a current source, which is I short circuit. So here's our current source. We have a resistor in parallel, as well as an inductor in parallel. So of course, this is Rn, this is L, and because the focus is this load, the current in this circuit is exactly the same as the one. So what we've done here is that we've did a conversion. We converted using the standard practices that we did earlier to do that. Once we've converted this, our circuit then is only this Norton circuit that we care about. So then there's 3 stages. The inductors complete response follows the same process as the RC response. And it has to go like this. Our focus now is the inductor. So now it's going to be IL of minus infinity to 0. we define that as 0 minus. This is the initial steady state. Now the switch is thrown. And when the switch is thrown, we're interested in from 0 to 5 tau. This is what we call the transient state. And then finally, if we let this guy go long enough, at t equal to infinity, we get exactly to the short circuit value. And you can just see here, as the inductor becomes a short, it shorts out the resistor, so the I short circuit must be the same as the inductor current. This is what we call the complete response. By the way, I should have put here that this is the final steady state. And once again, this is what we call the complete response of the inductor. And we can clearly see that there are 3 stages. So as before, there are 3 stages required to compute the complete response. One, we have circuit number 1. So what happens in circuit number 1? We calculate IL of 0 minus before the switch is thrown. Once the switch is thrown, we then have 2 circuits that we have to deal with. We need circuits number 2 and number 3. So now we calculate the Norton parameters. What are the Norton parameters? It's I short circuit Rn after the switch is thrown. And then finally, that is the complete response right there. But in the end, we're going to have to solve the circuit problem. And that's circuit number 4. In this case, we solve the circuit problem in the original RL circuit after t equal to 0, at 0 plus. So now that we've summarized what we've done before, let's go in and do what we did before. We want to derive the transient response. And of course, this has to be after the switch, right? So in this case, this is after the switch is thrown. So let's look at that. So I'm going to say that 1 starts with the original RL circuit and converts it into Norton form. I'm not going to go through the details as we did before, but if you convert it into Norton form, then that means I have a current source with I short circuit. I have my Norton resistance. And then I have my inductor in parallel. And our goal is this current I of t. So when I look at this circuit, we can clearly see that it's in all of these elements are in parallel. So we see here that this is a parallel circuit that requires two, I'm going to say observations for lack of a better word. One, we have to apply KCL to set up the first order equation and parallel elements have the same voltages. And if they have the same voltages, then that means here that VR and VL have to be the same, but we know how to write VL. So now if I apply KCL, we then see by looking at the circuit, we're then going to have that I short circuit is then going to be the current through the resistor plus the current of the inductor. And of course, they both change with the function of time. But the resistor has the voltage of the inductor. So this is going to be the voltage of the inductor divided by the Norton resistance plus IL of T. So now using the inductor voltage, I'm going to get a term that then reads L Rn dL dt, and that equals to IL. So when I'm looking at this, this is the result of applying KCL. But we have to isolate the derivative term. So putting this into proper form, we then see that this is going to be di dt plus IL divided by L divided by Rn equals L divided into I short circuit. So if you put this into proper form, one recognizes this form is exactly the same from the first order equation of the Thevenin RTHC circuit. In other words, this is also the same as this guy here in form, that is. So then everything that we did before can immediately be applied. So let's do that. So following a sequence of steps that was done to the Thevenin RTH first order equation, the complete response of the Norton RNL circuit is as follows. So now that we have that equation, we then start with our dummy variables. So we need to redefine our dummy variables. So we said, in this case, we're going to replace the capacitor voltage with the inductor current. We define a tau that's going to be slightly different, which is L over R over N. And then our K value is still going to be I short circuit divided by L over Rn. So if I do that, I could then go to the next step. I can write the first order equation. So now I have a first order equation. And what does that first order equation look like? It looks like dx dt plus x over tau is equal to the k value. So if that's the case here, then I could come in here and I could now go to the next piece here. We already know the solution of this, and this is the complete response. And when we wrote the complete response, we said that this was x of t is going to be x of infinity plus x of 0 minus x at infinity, all times the exponential term. Now all we have to do here is apply this technology to the Norton RNL circuit, where the complete response is then going to read IL of t, and it's going to be its I short circuit plus the initial value minus I short circuit times e to the minus t over tau, where tau this time is then going to be L over Rn. And this is our complete response.